Well. Boom.
Yes. Hi, everyone. I'm Sebin, and thank you for being here. Today, I'm going to talk about Columbia Glacier. So, Columbia Glacier is one of the world's fastest retreating tidewater glacier. So, a tidewater glacier is a glacier that terminates to the ocean. Since 1980s, this glacier has receded more than 20 kilometers. This sudden retreat has led to many scientific studies focused on this specific glacier. If you look at this time lapse, you can see by 2010, this glacier has separated into two different branches. One to the west, which is called the post branch, which is smaller, and the main branch to the east. One of the primary questions these studies tries to answer is whether this retreat is due to changing climate or due to a normal advanced retreat cycle of tidewater glaciers, which is normal for tidewater glacier to advance for a long period of time, then suddenly retreat over a course of time. But we don't know whether it's related to climate change, or there is some evidence that this glacier is retreating due to climate change, but not conclusive yet. Why this interest as a seismologist is because as this glacier retreats, icebergs from the terminus of the glacier can break off and fall into the water. Such calving events are strong enough to create noticeable seismic energy across the regional array. I emphasize on the word regional array here because none of the seismic stations are put forward here to address or learn about glacier quakes. They are there to learn and monitor earthquakes. However, these signals are strong enough to trigger or to make the analyst notice that, hey, this looks like a significant event. But they come as a noise in their regular everyday life. Hence, they classify it or label it as glacier quakes and keep it in the catalog so that it won't contaminate earthquake-based studies. And they have been doing this for many decades. However, we are not aware of any study which look in the long-term trend of these events and study what does it tell about the dynamics of the glacier. What does these events tell about the changing physical nature of the glacier? So that is the research question we try to answer through this study. We move forward. As far as an analysis is concerned, Columbia Glacier is no exception. Because Columbia Glacier is just one among many glaciers that produces events of this sort. We focus here on Columbia Glacier because it is one of the well-studied glaciers in the world. So there we have a privilege of having diverse data sets and wide literature. If we are able to establish that these signals can elucidate physical trends or dynamics of the glacier, then we can extend this study to many other glaciers in Alaska, and we can explore all other glaciers using the findings we do here in this study. And that's our long-term future objective. Saying that, let's now just focus on Columbia Glacier. And these red triangles are the seismic stations on which we record these glacier quakes from Columbia Glacier. The green circle is a weather station we use to look at the weather data. And the black dashed square right here is the part of the ocean where we acquire sea surface temperature from, which is also from satellite-based measurements. All right. Now, okay. I don't know why that looks like that, but it should look a little more clearly. But anyway, if you look at these events, this is the set of events which comes from Columbia Glacier, which is located in the original catalog. And if you look at these events, we see quite a bit of a spread. That is because this is not your typical earthquakes. They don't have a clear P or S arrivals. They have an emergent onset, which means locating them is not that easy. Hence, we see a spread around the glacier. We can improve the location a little bit using traditional relocation algorithms like hypodedy. And that's what you see here. And you can see that these events get constrained a little bit more towards the glacier once you relocate it. However, we already know this is coming from the terminus of the glacier from prior studies and prior direct observations. So the interesting part of this map comes from the fact that if you look at the spatial spread of these signals in conjunction with the terminus location of the glacier, which is color-coded by the origin time of the events and also the terminus location with time, you can see that this event actually move along with the terminus of the glacier, which is interesting and not surprising because we know this comes from the terminus, but it is also a confirmation of prior observation and studies that these events are in fact coming from the terminus of the glacier. Being that established, if you look at the temporal trend of the events, some interesting patterns pop up. We see no glacier quakes before 2010. They have a sudden onset in 2010. And if you look specifically within 2010, you will see these events start appearing around August. So it's a quite sudden of an onset. And after that, we record these events consistently through time. And we see a decline in events reaching its minimum in 2018, followed by an increase again by 2021 or so. We see a spike in 2014 as an exception to the general trend of the data. So the next question one would ask oneself is, how can we explain this trend? Let's start from simple hypothesis to more complicated, I wouldn't say complicated, but more interesting ones. So the first hypothesis that comes to my mind is that, okay, maybe it is something about the dictation capability of the network. Maybe fixed a station in 2010. Maybe we added one more seismic station in the region. Maybe somehow the dictation capability of the network is improving. It's not very interesting as a scientist, but it's totally plausible. So to rule out that, we look at the availability of the data of seismic stations on which we record these events. These percentages show how much of these events are recorded in each of these stations. Yes, there are gaps in the data, but there is no trend in the station availability that would explain a sudden onset in 2010, or a minimum in 2018, or a spike in 2014, or a subsequent increase after 2018. So we can rule out that possibility that this is due to increasing or changing network dictation capabilities. What would be the other reason for a temporal pattern to evolve like this? Maybe in 2010, here at Geophysical Center, we started paying more attention to glacier quakes. Maybe in 2014, the workload on seismic analysts were manageable enough that they could spend a little bit more time on glacier quakes so that they can catalog all of them. If that's the case, this change in protocols should not reflect in one single glacier. It should reflect across all glaciers because it's a common thing happening at the Geophysical Center, and that's not happening in any of these glaciers. In fact, in 2018, we see spike in many glaciers, other glaciers in Alaska, which explains these trends are not due to evolving cataloging protocol, fortunately. So we know now that these events are in fact actually coming from changing physical nature of the glacier or from the dynamics of the glacier. So now let's assemble whatever we can from the glacier to see or understand why there is a trend like this. The first data set we look at is the bathymetry of the fjord. So this glacier terminates to the ocean. So there is a fjord where this glacier terminates and it has a depth. And some part of this fjord is already occupied by the glacier. So we cannot go in a boat and measure bathymetry because glacier is already sitting there. So this data comes from two separate sources. One from boat-based measurement, in the part of the ocean where the glacier has already receded. Another from mass conservation-based modeling done by glaciologists. So I used these two data sets and combined them together to make a model of the fjord bathymetry. And I defined a transect across the center of the glacier and sampled the bathymetry at the intersection across the transect and the terminus lines. Why I do that is because we are only interested at the bathymetry in the terminus, because we know these events are coming from the terminus. If I do that, the time series will look like this. Okay. Now let's see what other data sets we can assemble. We can learn about the thickness of the glacier by looking at the digital elevation models in the region. And again, we are only interested in the region close to the terminus. So we define a 200-meter polygon at the terminus upward, and then calculate the mean elevation in these polygons, denoted by the gray line, and the whiskers in the gray line shows the standard deviation within the polygon. Okay, we have now elevation and the bathymetry. We can also look at the velocity of the glacier. So this is an GIF of a glacier from Greenland. So if you look at this glacier, this is satellite images. You can see this glacier is flowing like a river. And like your eye tracks the features in the glacier so that you can delineate the velocity of the glacier, we can do the same thing algorithmically. And this was already done for Columbia and many other glaciers in Alaska. So using this is publicly available. So using that, I extracted the velocity of the Columbia Glacier. You see quite a bit of variation seasonally. There's a large jumps in a year in the velocity of the glacier. That's because in summer, when everything melts, the water goes under the glacier and lubricates the glacier from the ground. So that means a lot of velocity. But in winter, when everything freezes up, glacier slows down a little bit. But looking beyond that trend, you can also see long-term trends in velocity. If you look at here, around 2018, the velocity of the glacier started increasing slowly. Okay. Moving forward, we can also look at the energy of these quakes, how much energy these glacier quakes have. So to estimate that, we use the station GLI. We choose this station just because its proximity to the glacier. And we calculate the power spectral density of each of these events, which is just a measure of its energy, the 1 to 3 hertz band, which is the band we know these signals have dominant energy in from prior studies. And that's plotted here. We also use sea surface temperature and precipitation data of the region. Now that we have all the data set, we have all the observation, let's bring all them together and make some conclusions about the glacier. Okay. Now, let's first look at just bathymetry. So, if you look the bathymetry of the fjord, along with the temporal trend of glacier quakes, one thing become obvious. Before 2010, the bathymetry, the fjord was quite deep. The glacier was in a deep part of the fjord. By 2010, the glacier receded to a much shallower part of the fjord. Now, from about minus 400 meters to minus 100 meters. So that's a big shallowing. And whatever that may be, that caused the sudden appearance of events. You can explain this sudden onset looking at this because they line up. If you look at the minimum in 2018, that can also be explained by the deepening of the fjord again, which you can see here. So these things nicely mirrors each other. So they correlate well. And after that, in 2020, again, the fjord shallows and we see number of events increasing. So why would that be? Why a bathymetry of the fjord affects the number of quakes we record in the catalog? This is a conceptual model explaining that. The figure A shows in a deeper bathymetry, the glacier is in deep water, that the water supports the glacier through buoyancy. So whenever a calving happens, the ice doesn't break off and fall into water, but the ice is supported by the water and it gently floats away. That means even though calving happens, we don't see it in the record because they don't fall into the water and create a cavity collapse, which is necessary for production of glacier quakes. However, when the glacier is grounded, the seracs or the icebergs can fall into water, forming a cavity, creating pressure waves, which then we record as glacier quakes. So that's the reason why we see a strong correlation of the glacier quakes with bathymetry. But bathymetry is not just the end of the story. There are other factors influencing the number of glacial quakes. We move forward, and if you look after 2018, you see the number of glacial quakes are steadily increasing after 2018 up to 2024. That's the end of our period we studied. Probably is increasing in 2025 too. And bathymetry couldn't explain it because that stays constant. what else is changing? If you look at the velocity of the glacier is also steadily increasing at the same period. So that might be the cause for the increase in glacier quakes. Why? Because if the velocity of the glacier is faster, that means one of these two things should happen. Either the glacier should advance because there are more ice going through to the terminus of the glacier. That's not happening in Columbia. Then what should happen? This ice should calve away, and that should result in more glacial quakes, and that's what we see in our data. So glacial velocity is also a factor that affects number of glacial quakes we see in the catalog. What else can we learn from these quakes? If you look at the energy of these events, before 2018, this cluster, on average, have a higher energy compared to this red cluster. So this is in decibel, so this is in log scale. So this difference is kind of important. This is not like linear difference. This is in a log scale. So when we think about it, we know that events before 2018 have a lot more energy than events after 2018, broadly. Why that might be? That can be explained if you look at the thickness of the glacier. At this scale, it is hard to discern, but before 2018, the glacier was approximately 50 meters thicker than in 2020s. That means in early 2010s or in 2010s, the iceberg was falling from a much higher height than in 2020s. If you throw a stone from much higher height to a water, that should create more energy. And that's what we see in the events. So we can dictate, we have some proxy. The energy of this quake is a proxy of the height of or the thickness of the glacier. What other things? If you look at the seasonal pattern of these events, you see two peaks. One primary peak around April, May, and the secondary peak around August, September. The primary peak, the one in the April, is due to increasing velocity, because in April, we know glacier accelerates a lot and it speeds up. The secondary peak corresponds or correlates with the sea surface temperature and the precipitation from the region. Why? But when the glacier is sitting in the ocean, if the water is warmer, of course, the water will melt or undercut the terminus. So glacier become more unstable and more calving will happen. When precipitation increase, the discharge under the glacier will increase, and that flow will entrain this warm water, again increasing the undercutting. So that might be the reason for increase in events in late September, concurrent with increasing sea surface temperature and precipitation. One thing I have not explained that stands out quite well in this data, which begs for an explanation, is the spike in 2014. We don't see any spike in any of these data set in 2014 that could explain this increase in events. But we have a hypothesis. If we look at the glacier more closely, unlike any other years, this glacier was temporarily advancing instead of retreating in 2014. It was also advancing from a deeper part of the fjord to a shallower part of the fjord. If you now try to make a mental picture of what's happening physically, you are actually pushing up a bunch of ice from a deeper fjord up to a hill and still pushing it. That should create some kind of, that might create some gravitational instability. That might be the cause of this increased number of events in 2014. We don't have any evidence to prove it, but this might be the case. So bringing it all together, the study demonstrates that existing catalog of Alaska glacier quake is sufficiently robust to observe patterns in glacier calving spanning past 2 decades. We see when the terminus shallows, the seismic events increases dramatically. This presumably reflects the transition to high Serac-driven calving, or the calving when this calving from the terminus by icebergs is called Serac, because the way they look, I think glaciologists call it a Serac, so that's what it means by Serac-driven calving. And we also see the surface velocity of the ice correlates with the rate of glacier quakes. We observe that some evidence that the taller glacier front creates higher energy quakes. We also observe correlation between late summer precipitation and sea surface temperature with increased glacier quakes. And that will be it. Yeah. Thank you.
I assume there might be a question or two.
Which points are they predominantly getting the splash of the ice into the water? Could some of that be due to motion of the ice along the bed of the glacier surface?
The glacier quakes we observe in the regional array, which is tens of kilometers away from the glacier, is studied and observed from the splash of the ice. There might be events happening from the basal friction. We don't believe that will be detectable in a seismic session which is tens of kilometers away.
These talk 7 was really cool. Earlier, when you were trying to justify the different mechanisms, you showed a comparison of 3 different glaciers and that they had a kind of spike on a similar year, but it seems like all of the reasonings you gave for this glacier were localized. I was wondering if there's some maybe regional trends or you thought about that.
There will be some regional trends, but this is not the complete data set because this is just a subset of the data set that makes it to the catalog. It is completely possible to use this data set as a training data set and explore and we believe that we can at least dictate an order of magnitude more events. Once we do that, then we can, I believe, elucidate, regional trends across many glaciers. I think that is the future direction of these kind of studies.
Thanks for your talk. I was interested in 2014. So when you zoom in on that year, at a different time resolution, that you can see really where in which month of the year the additional glacier quakes are happening. In the pattern, you can see them.
This is 2014. We see these events. There is 2 clusters, notably.
The 2 spikes that you talked about the springtime.
Yeah.
The spring melt.
Yeah. Yes. I want to look at it a little more deeper. I have not explored the implication of these 2 clusters because I feel this might be an anomaly, but I think, seems like that's the 2 spikes due to the increasing velocity and the precipitation and surface temperature.
Do you have a time series for terminus position and how I saw you have some, but it looked like just yearly. Do you have a denser time series for that?
I had created one, but I don't have it now.
Okay. I was wondering if you have terminus position and you have velocity, you can get an ablation rate from that. And then, that's going to be some combination of calving and melting, but it could be helpful to look at that in 2014. That there's like something happening, even if it's seasonal or something.
Right. Thanks.
Great talk. So you framed the talk surrounding 2 concepts, right? Is the Columbia retreat a climatic event, or is it a cycle that happens for tidal water affected glaciers? What does your research
She's not think about that. Yeah, I don't know. This study didn't make a leap in that action. We have to look at the regional trends over a long time across many glaciers to say any conclusion of such. This will be a first step, I guess.
7, can you go to your seasonal slide toward the end? The 3 plots.
Yeah.
While we're waiting, if our online audience has questions, feel free to dump them in the chat or just raise a hand and we'll make sure you're addressed.
Do you is it possible to try this out at the other regions in Alaska?
Yes,
It is.
it is possible.
Have you done it or no?
Yeah.
Okay. Because it seems like you would be predicting that whatever those trends are should be the same. Can you also comment? I was surprised at how many events still happen in the winter time, in the time when the glacier's not moving as much. But like the histogram at the top is pretty steady. Like it's not as strikingly seasonal as your velocity. I don't know. I guess can you comment on what's actually happening in the winter time? Nothing freezes over down there, or
I think the glacier is still calving in winter, even though not as accelerated in summer. The velocity, I don't think directly linearly correlate with the number of events.
Mhm.
We don't see that here. Yeah, I don't know if I answered your question.
The main one was just curious if this would work for the other glaciers. If it's possible, it'd be nice to see it. It would help your argument here, I think, if
Yeah.
it was.
It's worth pointing out, Ed and I were talking down at the screens at the other end of the hall this morning and just zoomed in on Columbia, and there's a nice little cluster in the last 2 weeks. Here we are in the beginning of December. So that's your off-season, steady, consistent background rate.
Say that the two lobes that you see in the count correlate with the two separate lobes in the average month glacier velocity versus, so you see kind of correlated.
Yeah, that's what I am saying. Yes.
Okay.
Yeah. This corresponds to this.
So from a mechanism perspective, they would be two separate mechanisms.
One's mechanism, but two separate contributing factors. Increased velocity will increase the number of quakes. Also, a stronger undercutting at the terminus also will increase the quakes because ice is gone. At terminus is thick, and if water is here and it is undercutting from the terminus, then the top part should collapse, right? So.
One more quick question.
Yes.
You mentioned at the beginning that kind of the motivation for the study was trying to determine whether the retreat of the Columbia was due to the typical advanced retreat cycle or climate. Do you have like any more to say there now that you've done the study?
No, I think I was saying, I think I explained a little differently. The motivation of this study is not about understanding whether Columbia Glacier retreat is due to climate change. But the motivation of this study is nobody is using this glacier quake catalog. We have decades of data. The motivation of this study to see if this data set is valuable to learn about glaciers, which it is. I think my study can tell about that. Next step would be to look at a long duration across many glaciers over a long time to see. Because I can maybe say, hey, look at this, but I have to statistically prove it. That's the hard thing about saying anything about climate change, because you only have data set for this much time. We need a long time series to say something.
So I think, and my memory's a little fuzzy, but there was a campaign. There were some campaign sets in the mid-2000s in Columbia. Was there any significant data recovered from that were useful in this study?
Yes, there are studies which put these regional campaign measurements, and this study, many of the assumptions we make for these studies build on that study, but that they are like a couple of months or part of a year. So yes, this study is built on observations made by such studies, but not directly influencing the results, I guess.
Can I jump on that question?
Yes.
Because you point out, right, there has been a whole raft of campaign studies at individual glaciers. So there's actually been two different seismic deployments at Columbia. One back 2007-ish and one quite recently. I've participated in some myself, and they've done a lot of work to address all sorts of things. But one of the things that became really clear out of those studies is, yeah, the big signals, those are capping. To Matt's question, yeah, there's also, I mean, glaciers, you need only stand next to a glacier to recognize how easy they are in many different mechanisms. All of those leave a seismic signal. But the one that's getting picked up, 200 kilometers away is this glacier calving. So all those little campaign studies have been great to help understand mechanisms like that. What they don't have is 20 years. This is not the ideal, this is not the perfect data set for studying a glacier. Gosh, would rather have something right next to it. But this is sitting there. This has that time history that is much harder to come by. What doesn't exist in those other studies. How did I miss that? Oh, Heather, thank you.
Hi, Seven.
So
Good job. I would say that just from, looking at the catalog myself and kind of keeping track of glacial events, there's a lot that we're not adding, and maybe consider doing some machine learning or something to add to the catalog, because there's a lot that we don't add, especially in you had in one of your plots a drastic decrease in glacial events starting in 2022. Depending on how busy the analyst team is, we may not be adding the smaller magnitude events, and that has decreased significantly the last couple of years, and that is because of changes in processing procedures. And that may also have contributed to the 2018 decrease, just because of activity elsewhere in the state. So I would suggest, seeing what you can do to make sure that the catalog is complete.
Yes, that's a future direction we can explore, but I think I disagree on the part that it might have contributed on 2018 minimum, because if that's the case, we should see a minimum in other glaciers too, because I don't think analysts will be, I don't know, correct me if I'm wrong, but analysts will be specifically not cataloging events from Columbia. We see a spike in 2018 in many other glaciers and a minimum in Columbia, which suggests that this might not be coming from changing catalog protocols, but real signals from glacier. And I totally agree with you that this is not the best way to do the study. You can design a machine learning method to train the data set and create a huge data set and look at long-term trends. Answering the questions related to climate change requires such a study. But as a first case scenario to show that these events are useful to study many things about glacier, I think this data set is a good starting point.
Anything else?
Quick one. That top figure, if you removed 2014 from it, would it look significantly different?
There are, yes, 2014. If I remove 2014, also this trend is there across many years. It's not just outlier trend. Yeah, I had that question. I had done that, but yes. Yeah, it's consistent across many years. Some years don't show it, but many years show it. So, yeah.
All right. Well, thanks again, Seb. All right. Thank you all. We will stop recording.